if you guys can come, make me really nervous. Oh, thanks so much.
Next time I will steal from my PI's office.
Awesome, yeah. Who's your PI?
Norton.
He's rich.
Why everyone
Let's
is
steal.
rich?
Yeah.
I'm poor. I'm a very poor guy. I have no money to buy the marker. So no matter what you can steal from your supervisor, it's more welcome to bring to the class. We still have 2 minutes. Karen, you mix. How was your long weekend, everybody? It's good?
Wasn't long enough.
Of course. Okay, let's start. For the last, to chapter 1, we still have some, I have one question, I have not the, one practice, right? I have not given the answer yet. So that is called what? Isothermal process. I asked you to calculate the work, right? Isothermal process, remember? So the process looks like this. So here's the cylinder, and then you have a piston here. Okay. So we have a gas inside, and then the temperature here outside is a constant, right? So the piston goes up or going down, doesn't matter. So it's going up or going down, doing work to the externals, and the temperature keep it a constant, right? So it's have the thermal exchange with this kind of we can call it heat reservoir or whatever. So it just a bath or whatever, a bath, just to keep it a constant temperature. So the question we're asking is, so if the volume of the pressure inside this tank at the beginning, initial state is Pi, I is initial, right? And Vi and Ti. And the final state, the piston goes up, right? The piston goes up. And the final state is the PF, VF, and TF, right? So the question is, what is the work, right? What's the work done by the piston? Remember, this is a question we have not answered yet. So we know that the temperature is the same, right? So it's not necessary for us to distinguish the final and the initial, right? The temperature just keep the constant, right? Then for the ideal gas, we know that the PV equals to nRT, right? Because T is constant, then PV is a constant, correct, everybody? Then we have this equation, P equals to nRT divided by V, correct? And what's the definition of the of the small amount delta over. What's the definition of it? PdV, right? And this one is what? Is nRT/V dV, correct? And integration from the initial state to the final state, correct? And then this one equals to nRT ln V final divided by V initial. That's it. Okay. And we have another thing we have not finished yet last time. We talked about, we call it the equipartition theorem. That we talked about the kinetic energy equals to half Vx squared plus Vy squared and Vz squared. I mean, we know that this equation is pretty long, so probably I don't want to spend too much time. So if I talk that one, we spend another 10 minutes. So I just post the process online, okay? I posted the entire process online so you can check. How can we call it equipartition theory. Equipartition theory means if for the energy, not only the kinetic energy, for the energy, for the total energy of the particle, you know that this can be written in that way, right? And for more complicated systems, we only have the kinetic energy, right? But for more complicated systems, sometimes we can also have this type of terms, okay? So different shape, it doesn't matter, okay? The equipartition theorem, is called equipartition. Okay, equipartition theory tells us as long as you have one of this kind of square, something square term, okay, as long as the term has this shape, no matter what it is, okay, it can be v squared, it can be xy squared, it can be something else squared, okay, as long as you have a square, each of this term will gives us half kT average energy, and gives us a heat potential of NT, okay? The molar potential, okay? So for the ideal gas, we only have the kinetic energy, 3 terms, right? Oh, I'm sorry. For each of the terms, give a half RT, okay? For the ideal gas, we have x direction energy, y direction energy, and z direction energy, right? That is what? That is half. Is 3 half RT. That is the potential. That is the heat capacity. What's going on? Sorry about it. That's the heat capacity of the ideal gas. Okay. But of course, the ideal gas is a small particle. It's only ball, right? So if we consider some other terms, for example, this is for the single atom molecule. If the molecule have this kind of shape, for example, like oxygen, nitrogen, you have 2 molecules, right? So it's not only move along x, y, and z direction, it's also rotate, right? It's rotating that way, it's rotating that way. It can rotate in this way, it can rotate in this way. But we do not consider rotating that way because this direction have no dimension, right? Then we have 2 rotation terms. So the 2 rotation terms give something like this. Okay? You don't need to know what's the meaning of it. This is rotational energy. But since it has this kind of square form, it gives us another 2 half R terms. That means for this kind of molecule, we also need to add another term. That means this one equals to 5 half R for the for the molecule has 2 atoms. Okay. Of course, this is rigid. Okay, it can also vibrate. The distance between the two atoms can change. Then we have some other terms. Okay, they become that's the partition. We're going to talk about it again if we have a chance in the class. But anyway, so that this I just want to let you know how can we theoretically calculate the thermal capacity of the gas and also the solid. Okay, for most of solid material we can also calculate that way. It's pretty precise. Okay. But for the we halfly done for the prove this theorem last time. Well, not fully done yet. It's very tedious mathematical process, so I'm going to post the process online. Okay. The other thing before we move on to the next chapter is there's I received some question online. The first question is, for the thermodynamics, we use quite a lot of the partial derivative, right? I have no idea whether you are familiar with it or not. Probably if you have finished your bachelor degree, I mean, probably know something about it. But if you're still an undergraduate student, or you have the more engineering, should be fine. But different background, probably are not very familiar with the partial derivative. But I think most of you know what is derivative, right? Or differential, right? So typically, for example, what I'm going to do is explain what is partial derivative. Okay? So think about it. If we have a function fx, okay, fx, y equals to fx, okay. So what is the physical meaning of df dx? Or we can write it in different ways, right? The first order derivative is df dx. What's the meaning of this one? The meaning of this first order derivative, this is y, this is x. So we have the curve. This one is fx. For example, if we calculate the derivative at this point, then the first derivative is just a slope. At this point, correct, everybody? That's a slope, right? This is. What about for equations have two variables or more variables? For example, z equals to g xy. Of course, we can put more parameters there. So you know that we cannot draw this kind of pattern in a two-dimensional frame anymore. We need to consider three-dimensional frame, right? X, Y, Z. Okay. For example, we have a curve. I just draw something like this. Okay. This is just like the torsion shape. Okay. It's the three-dimensional. Let me try it. A hat or whatever. Okay. So the partial derivative means, or be more precisely, partial derivative means we only move along the x direction, but keep y direction the constant, and to check how much the z direction change. For example, in that case, we keep y the same. So for example, I keep the y the same. This is the y the same, right? So we change x. Then you have what? You have this kind of curve. Correct, everybody? This is along the y direction. You just cut along this one, right? Then we do the derivative along this path. Okay, that is the slope on this one. Correct, everybody? And the same thing, if we do the partial derivative on y, but keep x the constant, then, for example, we move along this direction, then we'll calculate the slope along this direction. Correct, everybody? But of course, this is along y and along z, but along x and along y, but you can also align some weird angle, okay, along some weird angle. For that case, you need to do the derivative on both directions. Okay? But that's the definition of the partial derivative. Why we call it partial derivative? The reason is we only consider a portion of the function. We don't consider the entire function. Understand something? And of course, for this kind of for the function, we have multiple variables. We have no way to define the full derivative, right? It's not like this. Okay, but we can still define the small change or differential of z, something like this. Okay? You know what I'm saying? But we do not have something like this anymore. We do not have something like this anymore. Okay? We don't have something like this anymore. The reason is the z not only depends on x, z not only depends on y, it depends on both factors. Okay, that's the reason we do not write this kind of full derivative form. Instead, we use the partial derivative. Okay, but we still have differential. Okay, we still have differential. I hope I answered the question. Oh, by the way, the other thing is, some student asked me, so why, when we analyze some thermodynamics, we set some parameter at 0, but in other scenarios, we need to calculate more precisely to see how it changes. I mean, this question is very abstract. Honestly speaking, I mean, we cannot give you a more clear answer until we meet the specific problem. But when we talk about when we go to the specific problem, I will explain to you why we set the parameter to 0. Okay, there's no general answer, but we need to analyze the process case by case. And for example, for some cases, I'm saying that the delta Q equals 0. Okay, what's the reason for that? This is because we are talking about some system that thermally isolated from the environment. Okay, for example, we have a tank, and then for the entire tank, we wrap it with some thermal isolated materials, a foam or vacuum, whatever. So there's no thermal exchange between the container and the environment. That's the reason we set it at 0. Okay, but for some other process, we're going to see through the class, we cannot make this kind of assumption. And sometimes the delta W equals 0. This is because it doesn't do any work. Okay, it doesn't push the piston. Okay, to push air or some air to put, or we push the piston to compress the gas. Okay, the piston position just keeps constant, so there's no movement. Okay, if there's no mechanical movement, there's no mechanical work. Okay, that's the reason we set it to 0. Okay, I mean, if we set, I mean, there's no general answer why we need to set a parameter to 0, but it indeed depends on specific cases. Okay, we need to analyze one by one, but again, I will explain that when we encounter, this kind of assumption again. Any questions on first law of thermodynamics? No. This one. I saw somebody going to ask me a question. Anyway, so if no, we're going to move to the second law of thermodynamics. Okay? This is the second chapter. Okay? Or third chapter is up to you. But second law of thermodynamics. Okay? Second law of thermodynamics. So, in order to understand what is second law of thermodynamics, we need to first understand one concept. Okay? So, what is I'm trying to, when I prepare the class, I do not have this kind of small number, but I'm trying to give you this number to make the structure of the class clearer. Okay? First of all, let's have some discussion about spontaneous process, okay? And for this section, there's only logic reasoning, okay? Okay? I'm trying to give you a picture instead of math, okay? I'm trying my best to just here by talking, by explaining, give you an example to make you understand what is spontaneous process. And of course, the most important, what's the most important concept of thermodynamics, of the second law of thermodynamics? Anybody can tell me? Entropy? Entropy. Everybody agree with me? Entropy? Huh?
Positive?
What's that?
It's like always positive?
Yeah, entropy, right? I'm trying my best to tell you what's the entropy without involving any kind of mathematical process, okay? Try to see why we have entropy. Entropy probably most mysterious subject in the thermodynamics. What's the reason for that, right? Why we cannot understand. And honestly speaking, I don't like the textbook. I don't have the textbook with me. There's one chapter. Try your best to avoid that. It's not chapter, it's a small section, okay? Do not read that one, okay? That, besides making you more confused, it's doing nothing else. Anyway, we don't talk about the reason, okay? So what is spontaneous process? Anybody can tell me what is spontaneous process?
To happen in process, there is no need to external force or energy.
There is always an external force or energy. That's honestly speaking, okay? But let me tell you, ask a question, okay? But you're roughly right. I mean, if we need to have some external driving factors to make it happen, right?
Yeah,
Have your parents push you to study mathematics? Or push you to do some housekeeping work? Okay, do you think that housekeeping work happens spontaneously? Never. So what will happen if you do not do any kind of house cleaning?
yeah. Messed up.
Yeah, that's right. You become messier, right?
Yeah.
Entropy increase. So how do we decrease the entropy? You need to put energy in, right? That is not a spontaneous process. Okay. So that means it doesn't happen. It doesn't happen automatically. Okay, spontaneous process doesn't happen automatically. Okay. Give me an example. So we have the roller coaster here. Whatever. So you buy a ticket here. The ticket station. You buy a ticket here. You go to the roller coaster. You sit on the train. Do you think it's climbing to the top spontaneously? That's you pay for it, right? You need to pay the electricity to drive it there. But when you reach it here, what will happen? Just automatically going down, right? You don't need to give it extra force, okay? And then their business is done. Okay, their business is done. Then probably not done yet. There's some camera shooting some stupid picture and ask you to pay. Okay, but anyway, so you're going down, right? And all the following process spontaneous happens, right? So what's the reason for it? So what's the reason why the roller coaster can go downhill spontaneously?
Depending on
Gravity.
The potential energy reserved there that is getting utilized to get the kinetic energy.
Yeah. More generally speaking, so what is how the spontaneous mechanical process happens? So what's the driving force, or what's the driving factor for the spontaneous mechanical process? I'm not talking about thermodynamics, right? I'm talking mechanical process.
Gravity.
Not only gravity. Why it's not only gravity? Something else. I mean, more generally speaking. You already mentioned that. It's not gravitational force. It's what?
Storing of energy?
It's energy, right? It's energy. So then the object always prefer to stay in a low energy state. Correct? I think nobody of you want to stand up for all the time, right? You want to sit. And compare with sit, sleeping in the bed is more comfortable. Correct, everybody? The same thing. Okay? We know that for simple mechanical system, spontaneous means means the energy going down. Correct? But why I'm emphasizing the simple mechanical system? One body, two body, right? We already mentioned in the first talk. Three body system, I have no idea. Okay? You know what I'm saying? I have no idea. Probably the same. Okay, four body, five body, probably the same. Okay? But this is always the case for the thermodynamic system. Or be more precisely, I'm not talking about thermodynamics. I'm talking about one body, two body, three body, whatever. That's a simple mechanical system, okay? Okay, let me give you another example. Let me make the process more complicated, okay? Make the process more complicated. Right now, we think about the many-body system. Many-body system, of course, energy is still there, right? Energy is still there. But the question is the energy the only driven factor for the spontaneous process? Or in other words, will the many-body system always prefer to stay at the lowest energy state? You have no idea, right? Or I think my question is very abstract. You have no idea what I'm talking about, right? Let me mix. I mean, again, do not talk about thermodynamics. There's nothing about the mathematics. Okay. How many of you are parking in the garage today? Which floor are you parking?
Two.
What about you guys?
First,
First, what about you?
third,
When do you come?
9,
What about you?
like 8:30.
What about you?
9.
9. Why this guy, this lady and that gentleman came at 9? They occupy the first and third floor. But that lady came even earlier. He occupied which floor?
Third.
Third floor. What's the reason for that? Think about it. Here's the parking garage, right? For example, on the first floor, we have 3,000 space, okay? But definitely not, okay? I don't think UCL has huge parking garage. On the second floor, we have 3,000. On the third floor, we have 3,000 parking spots, okay? No parking spot reserved, okay? There's no employee, faculty, staff, everybody can use the, can share. Huh?
Imagine that.
I'm just, this is the model, okay? Not the real case. I think they should reserve some for faculty like me. But that doesn't happen. Anyway, think about this. Somebody before 9, 8, I mean, most of the spots got occupied. There's only one. This is the entrance, okay? This is the entrance of the exit of the parking spot, okay? And then the empty spot is hidden somewhere. You do not know where it is, okay? You drive a car through the first floor, enter the parking garage, okay? Right now you have only one car going into the parking spot. Okay, there's only one parking spot left over in the first floor. Do you think you will be able to find that spot? You definitely can. You just wander around. You can find it. But you only have 1 minute left of the class, otherwise you'll be late. Do you think you still park in the first floor? And the second floor is totally empty. What do you do? You go to the second floor, right? What's the reason for that? The reason is you know the possibility for you to find the only and the single vacancy is very low, right? But on the other hand, as long as you make some extra energy, go to the second floor, you will find the fully empty garage is waiting for you. You can pick up whichever you want. Correct, everybody? So the possibility, consider, the possibility you find a parking spot on the first floor compared with the possibility you find on the second floor. What's the ratio between them? It's 3,000 to 1, right? But which state has higher energy? Of course, you have this state have higher energy. You go to the second floor, you need to drive, you need to waste some gasoline, right? This state have higher energy, right? You prefer to stay on the first floor. The energy is lower, right? But this state has a lower possibility than that. right? That means the high energy state have 3,000 the possibility for the entire system to have a high energy is 3,000 times higher than the low energy state. Correct, everybody? Is that true? That's the reason you're parking on the third floor. You pick up the high possibility state, right? This is thermodynamics. I mean, this is dynamics. Okay, this is statistics, right? It happens every day. Don't think thermodynamics is very abstract. I mean, do I understand what I'm talking about? I mean, no. It's just like the statistics. Okay, it happens every day. That means for the many-body system, the energy definitely is one consideration. Correct, everybody? The other thing we need to consider is what? Is the possibility, right? Which they give you a higher possibility, right? When I use P, okay, I just put the possibility. Okay, possibility. But the Y energy still make some contribution. This is because if you have a lot of vacancy on the first floor, you still park in the first floor. You do not go to the second one, right? Understand something? As you have more and more free space on the first floor, you prefer to park in the first floor, and that means this ratio drop. Okay, as long as this ratio drop, this one dominates. As long as this possibility goes down, going up, this one dominates. Correct, everybody? So you have a competition between energy, or not competition, is composition between energy and the possibility. Correct? So basically, this is some of the second law of thermodynamics. But anyway, so we need to make a more clear and more strict mathematical expression. Okay? Did that make myself understand? Okay? The spontaneous process. For the simple mechanical process, we only need to consider energy. But for many-body complicated system, the energy is not only the driving factor for the spontaneous process. We also need to consider the possibility or which state is more preferred than the other state.
So the idea is that there'll be more energy where there's more possibility?
It depends. It depends. I mean, for this very specific example, yes. But for other systems, probably not the case. But for most of the scenario, what they're saying, right? Okay. Actually, the thermodynamic system behave roughly the same to the parking garage model. Okay? Just keep in mind if in the future you got confused with the statistics. Okay, whatever, the gas, solid, the gas cylinder, or gasoline or engine, just a parking garage. Okay. Okay, so let's go back to thermodynamics. Okay. Remember the parking garage model? Okay. Now let me give you some examples. Okay. The actual example in thermodynamics. Okay. Examples in thermodynamic systems. First of all, let's consider that one. So we have two containers. They are linked through a tube, okay? Through a tube. They are linked through a tube. And in between, we have a valve. In between, we have a valve, okay? We shut down the valve. And in this one, we have gas A. And in this tank, we have gas B. They are separate. All right, everybody? Right now, I turn on the valve. I turn on the valve. What will happen?
Equilibrium.
Equilibrium.
Of pressure.
Yeah. It's so professional expression. Nobody understands. They just went to each other, diffuse, right? One, again, we are not in the physics department, we are in engineering department, okay? We should not flow in the air. Okay. talk something, we speak some the native human language. Sorry about that. Yeah, probably people from different places will be like, this guy really fancy. Why do you just keep kicking me out? There's no parking spot for this guy anymore. Anyway, so A and B will go, A will go to B, and B will go to A, right? And this process is called, okay, I stopped talking about human language. Again, this is called diffusion process. Okay, diffusion. But the final state is the equilibrium state. Oh, by the way, so we talked about equilibrium. What's the definition of the equilibrium? What's the definition of equilibrium? Equilibrium means no further spontaneous process is going to happen anymore. Okay, equilibrium, that's the end of the spontaneous process. Okay. Anyway, so diffuse. Okay. So what is the final state of the diffusion? A and B mix evenly, right? No matter where you stay in this tank, no matter where you sample this tank, you have roughly A and B have the same, the ingredient, correct? Although you probably have 1 or 2 molecule difference. Globally speaking, that's the same, okay? Do you think this kind of diffusion is a spontaneous process?
Yes.
Yes, right?
Yes.
Do you think the energy change? There's no energy change. Because none of them doing work to the externals. The internal energy change. That means the U just a constant, correct? So what's the driving factor for this diffusion or spontaneous process? We're just talking about it. Forget about entropy. We have not introduced entropy yet. The possibility, right? The possibility, right? You gotta think about it. So definitely the A and B mixed evenly has a higher possibility than A and B separate. Correct, everybody? So then the driving force is the possibility. Correct? Did I got my point? So this is the spontaneous process. The reason I'm talking about this example is, in this kind of extreme case, energy is the same, but possibility is the driving factor for this kind of spontaneous process. Okay? But on the other hand, do you think A and B after mixed to each other, they can reverse the process?
No.
That A and B spontaneously separate is unlikely happen, right? Unlikely happen. You know what I'm saying? There was a joke. That is not a joke. It's kind of like a very interesting question. So probably Chinese people know. I have no idea whether you know. So you're cooking, make some cooking in the kitchen. So in your pan, you have red beans and green beans. After cook, how to separate them? You mix the red bean, and you mix the red bean and green bean together in the cooking pan. After cooking, how do you separate them?
Density.
Of course, if you cook a lot of beans, you cannot separate it, right? But you only cook 1 red bean and 1 green bean. It's not really separate. Okay? Anyway. Oh, very stupid joke. Anyway, but right now you know that it can't happen spontaneously, right? Okay, another example. So we have one metal, okay? Is in temperature of TA. The other metal in temperature of PB. Okay? We put them together. They have started having the thermal exchange, correct? And what's the final state? They reach the equilibrium, right? They reach the equilibrium. Correct? So what's the equilibrium mean for this case?
Temperature becomes same.
Same temperature everybody will be done? Not really?
Well, the specific heat capacity each
No, I mean,
slightly different, so it's
Yeah.
the total energy of the system is going to disperse, but the temperature amount would be the same.
Yeah, the temperature should be the same, right? Think about it. You jump in the swimming pool, you cool it down by the water, right? Although you're a totally different object. Right? One is water. Human body, most of the part also water. Okay? But eventually they reach the common temperature. Right? They reach the common temperature. Okay, if you have two objects put together, eventually they reach the same temperature. What's this called? What's this theorem called? If the object put together, they share the same temperature. There's a theorem. How do I know? This is called the zero law of thermodynamics. Okay. Remember? Okay. It just tells us there's a parameter named temperature. Okay, when two objects together, eventually they reach the same temperature. Okay. Basically, the first zeroth law of thermodynamics just tells us the definition. It's not the definition of temperature. It tells us we can define a parameter called temperature. Anyway, so they reach the same temperature. Again, do you think the total internal energy of this of the system composed of A and B changes through the thermal exchange process? No, right? It's still constant, right? So what's the driving factor to make this kind of spontaneous process happen?
Difference.
A different temperature, I mean. Another one, we already mentioned about twice.
Probably.
About the right? Do you think that this object, all the heat can spontaneously flow from one part of the object to the other part, and cooling down one part and warm out the other part? It doesn't work, right? This process doesn't happen, right? It's only reach the common temperature. Instead, the temperature doesn't separate. Correct, everybody? Understand what I'm saying? Okay. And then the driving factor is still possibility. Okay, so through this two thermodynamic example and one garage analogy, we can find some common feature. Okay, we can find some common feature of the spontaneous process, right? There's some feature of the spontaneous process. The first feature is the first one is at the beginning. The system must deviate from equilibrium state. Correct? If we already reached the equilibrium state, no further change will happen. Correct? And the second one, for statistic system or many-body system. Many-body and statistic system roughly the same thing. The reason why we call many-body system statistic system because we cannot detect the motion of each of the particle anymore. Instead, we only care about the statistic behavior. Okay, so basic statistic system and many-body system refer to the same thing. Okay? Actually, the second one more important. Keep in mind, okay? Energy is not the only driving factor, is not the only factor driving the spontaneous process anymore. Correct? And we're talking about the other factor that driving this process is the possibility. Correct, everybody? And we know that one state, the ending state, or the final state has high possibility than the initial state. Right? But the problem is, what kind of possibility? What's the expression of it? What's the mathematical expression of it? Right? And what type of possibility it is? Right? It's not like you flip the coin that you know that the head and tail have the half and half possibility. But for the many-body system, how we define the possibility? Correct? We don't know. We need to find a parameter in order to quantitatively describe the possibility. Correct? So that's the next job we're going to do.
Can you please repeat what means many body system? Suppose a metal piece. It
Yeah.
is many body or single?
It depends on the, okay. For many body and single body, it really depends on what kind of property you want to analyze the problem. Okay? For example, a piece of metal, if you're talking about thermodynamics, the heat capacity, heat exchange, or something, we're talking about the atomic motion inside it. Then you definitely have a lot of atoms inside this. But if you care about, if I throw that piece of metal, what the trajectory looks like in the air, it's a single body, right? Because all the atoms moving exactly the same thing, exactly the same, right? So we only need to. It really depends what kind of property you want to talk about. You know what I'm saying? For example, if you talk about the economy in the country, we have how many people in the United States? I don't know. But it's definitely a many-body system, right? But if you're talking about the Earth orbiting about the sun, do you think the behavior of a single human being affect that much? No, right? We only need to consider the Earth as a whole piece, right? So that's a different piece of mind. But it really depends on what kind of a problem you want to solve. Okay? All right. So let me see. Okay, then we go to the second topic. Okay, we're looking for the other, or another. I don't know. We don't know yet, right? Whether it's the other or another, we don't know. Really. Okay? The reason I'm saying that the other or other because we don't know whether we have only one factor or we have multiple factors. We don't know, right? This is the problem that people facing probably 100 years ago. At the beginning, we only know the Newton's law, correct? First, second, third law. Okay? The first law tells you the momentum, not momentum, inertia. Okay? The object always moving along the straight line at constant speed until there's the external force exchange kind of like state. And second law tells you F equals ma. And third one tells you that the action equals to reaction, but in the opposite direction. Correct? Understand what I'm saying? This is Newton's law. Okay? But when facing the thermodynamics, we find that again from Newton's law, we know the energy, we know the momentum, we know a lot of parameters. And then we will go to this kind of gas or whatever. People find that okay, the energy is not only driven force I will just mention. Right? The energy doesn't change by the why this process happens spontaneously. I already mentioned there's another driving factor. What's the factor again? Possibility, right? Possibility, right? So you can see, but we don't know the factor yet. But through the discussion, we spent about 40 minutes to discuss this problem. But you can see right now, we know this is this kind of factor or this kind of this factor has the behave like the possibility, right? It's more like a possibility. It's more like the statistic behavior. Correct, everybody? We are talking about the many body system. Okay. The first one is it has a statistic behavior. Or property, okay? It's a statistic behavior, related property. Correct? And the second one is not included in Newton picture. That means your classical mechanical picture do not include this property at all. So you cannot find this parameter in your mechanical textbook or from Newton's law, from your daily observation. Right? You cannot understand the thermodynamics from seeing the orbital of the Earth or without sign. You know what I'm saying? You cannot see that. And you cannot find from the textbook. Right? That's the reason why people got really confused. Most of people got really confused about what's the entropy is and what's that one. Okay, why we cannot find this kind of object in the mechanical textbook? Because it's not related to that one. Correct? We are talking about the many-body system. It's not included in Newton's picture. Huh?
What would for the statistic part, what would a good example of that be?
Let me give you some example. That's the next job we are doing. We're only talking about statistics, but I have not. We know that it's related to the statistics, but we do not know what specific, what the factor specific looks like. Right? We only know it's a statistic behavior, right? It's discuss the possibility for the state, but we don't know how to describe, how to find this parameter yet. Correct, everybody? So that's what we're going to do right now. Okay?
What does statistic behavior mean? Where are you getting at?
Okay, so that means the driving force is not only like the energy, it's a possibility.
Yeah.
You know what I'm saying? The state, that possibility is a statistic here, right? We need to go through all the possible states and find the one which has the highest possibility. We need to do some statistics first, right? And because of that, let's talk about something like we talk about statistics. Because of that, you will find that thermodynamics is not only, although we call it dynamics, but we use thermodynamics. The area can be, we can use this knowledge. It's far beyond like the water, gas, metal. You know what I'm saying? You can use the thermodynamic knowledge in the economy system, right? We can use this one to talk about telecommunication. Have you heard about the information entropy? Right, information entropy. I will tell you some story about the information entropy. So therefore, the data communication, they borrow some concept from thermodynamics. For the economy systems, you can do the statistics. Okay, for example, think about it. Exactly the same thing. The parking garage. I can even write down I can write down the distribution function just based on thermodynamics model to predict how the parking garage looks like today. Okay? So exactly the same thing. What's the reason for that? This is because this kind of statistic behavior not only apply to the gas, to solid, it applies to any kind of body system. Okay? So our job is just to include this kind of statistic behavior into our mechanical system. Okay? That's the reason we call it thermodynamics. But anyway, so that is still too much. I know there's a question. Let me answer this one first, okay? What it looks like. But first of all, we know there's some factors, okay? And the other thing is, we should be able to use this factor. I didn't write it down. And this one should be this one should drive the spontaneous process. Correct, everybody? This should drive the spontaneous process. But still, remember that so far we have not talked anything about mathematics yet, right? Let me see what I write here. Okay. I think I cover all the information. All right, so it should drive the spontaneous process. And the other thing is, the other requirement, not requirement, but preference, okay? This parameter, or this factor, should better be thermal okay. This factor should better be or should be better. It doesn't matter. Should be better or should better be. What's the difference? You can tell me. I'm not a native speaker. This factor should better be a thermodynamic parameter. What's the reason for that? The reason is, if it's a thermodynamic parameter, we can calculate it, right? Remember, we're talking about, for most of the scenario, it's really hard for us to calculate Q, for us to calculate W, because it depends on the process, correct? But if this factor, statistic factor, is a thermodynamic parameter, it's determined by the state, independent of the process. Correct, everybody? Then by compare two states, we can know whether the system can evolve from inert state to the final state. We do not need to care about the detailed process. Just by comparing initial and final state, we can know whether this process or any kind of process can happen spontaneously. Correct, everybody? So this is the preferred, requirement. Make sense? Does it make sense?
When you say factor, do you mean possibility?
The factor related to the possibility.
Okay.
Okay? You know this entropy, okay? But I just do not want to tell you this is entropy, okay? Because this is the logic of reasoning, okay? If I'm telling you this is entropy, it just makes everybody very confused. But through the logic analysis process, you will know the feature of it, okay? I want the entropy appear naturally instead of just squeeze this kind of really awkward concept in your brain. You know what I'm saying? But you can understand all this thing, right? This happens naturally, right? Except the last one. This is some definition, some preference, okay? It doesn't happen naturally. But for other part, it happens naturally. We want to find a parameter related to the statistics behavior of the system and can help us to analyze the spontaneous process. And it should be better the thermodynamic parameter to ease our work, right? And of course, it's not included in the mechanical. The third Newton's law doesn't include this parameter, okay? But again, so then our job is according to this feature and look for the parameter, okay? Looking for this parameter related to the statistic behavior, okay? And how can we find it? Just do some practice, okay? Some practice. Okay, the reason why okay, so let's try to analyze some system to find whether we can find this kind of parameter or this kind of factor, okay? For example, if I put a tank, a sealed tank, okay? In the reservoir, okay? In a temperature reservoir, okay? The reservoir has a constant temperature, T. Okay, it's infinitely large and has the infinite amount of heat inside it, okay? And just keep a constant T, okay? And then we have some gas trapped in half of the cylinder. Okay? And this is solid tank. And somehow, don't ask me how it happened, but somehow we remove the separator in between, and then the gas have the free expansion process. Correct, everybody? So did we have this free expansion process? Right? This is a free expansion process. So then, let me write in. Probably, this is the initial state, And the final state looks like this. This is the final state. We know that this process is spontaneous process, right? And we want to know which parameter change. Do you think the temperature change in the cylinder? No, right? We already mentioned, because for the free expansion, there's no external work, and then the internal energy doesn't change. And for the ideal gas, the internal energy only depends on temperature. If the internal energy doesn't change, the temperature doesn't change. Correct? Then from the initial state and final state, they share the same T. Correct? They share the same T. And PV are different. Right? PV, of course, are different. But we know that P times V, they're the same thing. But we already know that P and V, they cannot be used to decide the state, right? They are not the thermodynamic process related to the statistic behavior. They are mechanical parameters, right? P and V are mechanical or geometry parameters. They are not related to the statistic behavior, right? So we know that T doesn't change, so it's definitely not the factor can tell us whether the process happens spontaneous or not, okay? And P and V, this is mechanical, no, this is just the geometry, right? But we cannot find it, right? But so far, we cannot find any kind of factor decide whether spontaneous happen or not through this parameter yet, correct? And the question is, what the factor looks like. Remember, for the last requirement, we prefer this factor or statistic related factor to be a thermodynamic parameter, right? For the thermodynamic parameter means it's only determined by the final and initial state, correct? Although it's really hard for us to draw this kind of process in the figure. For example, you have the P, you have the V, okay? This is the initial state, this is final state. We do not know how this kind of free expansion process happened on this kind of PV diagram. We do not know because it's just very quickly and suddenly because it's not during the process. The gas is not in the equilibrium states. Okay, it's very fast and everywhere they're not the same, right? But since we are looking for a thermodynamic process, we can find a virtual process. We can just build up the process to link these 2 points, and then to calculate the factor. Although we don't know yet what it is yet, right? We can find a process to link these 2 points through a thermodynamic process, correct? Because we want this factor to be a thermodynamic parameter, which is defined by the state only, right? Okay, so based on this kind of the idea, let's reconstruct the process, okay? We do not know the free expansion process, but we can build something like this. This is a cylinder. We put a piston here. And in the initial state, the pressure for this one, the pressure is Pi, Vi, and for here, the same thing, Pi, Vi. Okay? And then, we move the piston up. We move this piston up to the final state. Okay? To the final state. And then the volume is a Vf. Okay? For that one is the Pf Vf. Okay? And during this process, we know that because it's doing work, then this kind of gas inside the cylinder will absorb some heat from the external reservoir, correct? Is that true, everyone?
Expanding?
It's expanding and doing some work. Right? What's the work? delta W equals to P dV, correct? We just talked about that at the beginning of class, isothermal process,
Yes.
right?
Yes.
And it observes some Q, right? Because it's just a barrier inside this kind of reservoir, the inherent temperature of the system doesn't change.
So the temperature outside the piston is higher than inside the piston?
No, they are the same. It's just like piston in the room. So if you take it up, warm it down, the room temperature doesn't change. You know what I'm saying? Because the heat capacity of the reservoir is so large.
Okay.
Okay? The temperature doesn't change. The temperature doesn't change is what? The temperature doesn't change means the du equals 0. Correct, everybody? Then the dq should be equals to dw. Delta q should equals to delta w, right? And what's that? Remember we were talking about, right? This is nRT v dv. This is what we mentioned, right? Then the total change through the entire process, the change or the thermal exchange or heat exchange through the entire process, just do the integration, initial to final, nRT v dv. Okay? Then this is what? Is the nR T long V final V initial. Right? V final V initial. Compare these two processes. The free expansion process and isothermal process. You can see that the initial and the final state are the same, correct? But the processes are different, right? The initial and the final state are the same. I'm talking about initial and final state only to the cylinder inside, okay? Are the same, correct, everybody?
How is the state the same?
Because, I mean, think about it. The pressure the same, the volume the same, right? The initial volume of the two systems the same.
Yes.
The final volume of the system, we can make them the same, right? And all of them share the same temperature. Hmm?
Here,
When we're looking at volume, are we looking at the particles or like the volume of the tank?
The tank, the volume of the tank.
So is it then the particles occupying the space of the tank?
Yeah, it's fully
So
outside.
in that case, wouldn't the volume be 1/2 and then 1?
No. I mean, we put some separator in the middle first.
Yeah, so wouldn't
So we
that
just
volume-
confine the particle at the bottom, a half bottom of the tank.
so
at the beginning.
So the volume would be 1/2 and then 1?
Yeah.
Okay, so the volumes are different.
Yeah, volume different. But for that one, the same thing. At the initial state, we use a piston to confine the particle in the bottom half of the cylinder. So the volume, the same. I'm not talking about the volume of the tank, I'm talking about volume of the gas. They're the same, right?
Okay.
And the final volume the same,
Yes.
right? And temperature also the same. So pressure definitely the same. So that means for the free expansion process and isothermal process, the initial state are the same, final state are the same. But the detailed process are different. One is free expansion, the other is isothermal process. Right? Because the isothermal process is what? It's because we can draw the isothermal process on this kind of figure. Then we can do some calculation here. We can calculate the delta Q, how much heat got absorbed and how much work done, right? But for that one, we can calculate nothing because we cannot draw this kind of PV diagram, right? That process is very random. We don't know what happens, right? But anyway, so since we are looking for the factor only related to, we are looking to the factor that to be a thermal parameter, a thermodynamic parameter. So it should be defined only by the initial and the final state, independent of the process. So we can borrow this kind of calculation to analyze the property of this process as well, right? And look at this equation. Look at this equation. So we have what? We have the delta Q equals to nRT ln Vf V. Correct, everybody? All right, so that's the only thing we can calculate from the system, right? Something else? Nothing else, right? We cannot calculate anything else. right? That's the only thing we can calculate. Because this system is so simple, right? You can see everything is there. Volume, temperature, and we know that the delta Q equals to delta W. That's the only parameter, that's the only information we can get out of the system now, correct? And we already know that this one, delta Q, is what? It's the integration of the delta Q, integration of this delta Q through this kind of the path, right? But we know that the delta Q is not a thermodynamic process, the thermodynamic parameter. It depends on the process, right? So this factor, delta Q, definitely not the factor we are looking for. Correct, everybody? And this one is constant, this one is constant, right? And this one is a geometry parameter and different from system to system, right? So the only thing we can do is just like doing something like this. Okay? I'm not saying anything about it, okay? This is just delta Q divided by T. So what does that mean? We don't know yet, right? We don't know what's the meaning of this parameter yet. Okay, but let's do some analysis to see how this parameter behave. Okay, how this parameter behave. Everybody follow me? Can you follow me what I'm saying? Yeah, go ahead.
We are doing it like without considering the atom or expansion. Like,
We're considering expansion. I mean, they are both.
yeah, because even if it's free expansion, right?
Yeah.
There will be change in temperature, right?
No.
No.
The free expansion doesn't change the temperature. We're talking about this one.
But let's say the separator, the membrane, right?
Yeah.
If we have a membrane and there is no friction, it can move, let's say. Does that free expansion happen?
Yeah.
So if it happens, that means there is some pressure, right?
The reason is you have some pressure. For example, this is membrane can move freely. You have pressure go there. You have distance, but on this end it's vacuum. It's just like I'm pushing my hand to nothing. So you are not doing any work. You know what I'm saying? You are pushing your hand to nothing. You have to push your hand.
Ideal case.
Huh?
Vacuum, right?
That's the ideal case. That's the ideal case. But no, vacuum is not ideal case. The vacuum is this. I'm talking about ideal gas. But if you're talking about real gas, the temperature can change. That's how a refrigerator works. You have expansion, it's cooling down, right? But I'm talking about ideal gas. You have free expansion, temperature doesn't change. Okay? Other points? Any questions? Okay. So if you have no questions, let's look at this behavior. Okay? Let's look at the behavior of this parameter. Again, we compare this to, we compare this process. So we know right now we find a new parameter. We don't know what it is yet, right? We can write it down in another shape. We call it the DS. And I'm not saying what the name of it yet. Okay? Is that all right, everybody? Okay, let's see does that parameter make any sense or not? Right now, the difference is, right now we consider the reservoir and the tank as a whole system. Okay? Previously, when we do the calculation, we did not calculate the change of the reservoir. We do not consider the reservoir, right? But right now, let's take the reservoir into account as well. Okay, we know that in that process, this cylinder absorbs some heat from the reservoir, correct? Then, for the cylinder, this delta S equals to what? Delta Q divided by T. T doesn't change, right? And for the reservoir, Is that spelling correct? Reservoir. What's the delta S? Is lose some heat. Is lose some, give some heat, correct? So you have negative sign there, right? Correct, everybody? Then the total. We just sum them together equals 0, correct? Is that right? Okay. Let's go back to that one. There's no thermal exchange, okay? There's no exchange. Because the temperature doesn't change. There's no heat exchange between the reservoir and the tank in this case, correct? But as I mentioned, this parameter is a thermodynamic parameter, okay? What's the reason? Because for this specific case, this one equals to NR times ln V final and V initial. So this is only defined by the final state and the initial state, right? And for that case, for the cylinder, the same thing. Although the processes are different, but for cylinder, we still have delta S equals to what? Delta Q equals to delta Q. Right. Although there's no delta Q in this process, but probably not in this. Probably write something like this. Still equals to NR. Correct? Still equals to this one, right? Because the initial state and the final state are the same. Correct? Then this parameter should be the same. Is that true, everybody? And then let's look at the reservoir. Since there's no heat exchange, the delta Q equals to what? Delta Q equals 0. And this term equals to 0. Correct, everybody? And then what is the total? Correct? And you can see that right now we see some difference. Okay? For this isothermal process, the change of S are the same for the cylinder in the other isothermal process and free expansion process. Correct, everybody? For the cylinder, they have the same change in the S. Correct? Because it's only defined by the final and initial volume. But for the reservoir, there's something different. For the free expansion process, the reservoir does not have external exchange with the cylinder, then the S doesn't change. We have the point equal to 0. And the total change of S equals to the change of the in the cylinder, right? Is this term. Correct, everybody? But for this one, because you have the thermal exchange, then the total change of S equals 0. Right? In that case, although we don't know what's the meaning of the S, but from this example, we can see that this parameter, delta Q divided by T, can help us to distinguish these two processes. Although the final state looks the same, but because the paths are different, we can find there's a parameter called S are different. You know what I'm saying? And what's the name of the S anymore? And anybody tell me? Yeah, entropy. Okay. Do one practice, okay? Right now, we give it a name, okay? Okay? Entropy, what's the meaning of it? I don't care, I don't know. But I only know the definition is delta Q by dt, okay? That's entropy. For the spontaneous process, the entropy is larger than 0. For the reversible process, the delta S equals to 0, okay? So that's one conclusion, but we're going to further, but this is only from this very specific example. We haven't proved this kind of principle can be applied universally to other thermodynamic systems yet. But for this specific case, yes. Okay? So for the next time, I'm going to prove it. Okay? This parameter is a universal parameter applied to all thermodynamic systems. Okay?
For the isothermal,
Class is done. Okay? So I think I'm going to answer your question.
for the isothermal process, it means temperature remains the same, right?
Yeah.
In that case also I see the temperature is same.
The reason for this one temperature is same is because the gas do not do any kind of mechanical work. Okay? If there's no mechanical work, then the temperature, then you do not change the internal energy. If the internal energy doesn't change, the temperature doesn't change. Okay? That's the argument. It's not like this. This one we just put it there. I mean, you have thermal exchange. But for that one, we do not need the thermal exchange. Okay? Because the temperature automatically keep constant. So the statistic behavior of S is the discussion is a task of the next chapter, because the statistic explanation of entropy. Okay, that is the chapter 3.
Question about the last.
Yeah.
I was wondering, would the Q be negative in this case?
Oh, yeah.
Okay,
The
so
truth
it's
is, yeah.
positive sign.
Yeah. The reason is that depends on the. I was about to say that, but since everybody talk about the VD, I mean, I just ignore it. Yeah, you're right. It depends on which one you select.